Okay, right. So good evening, class. So let's start our tutorial. So we'll first start with a summary on the confidence interval. All right. So let's talk about confidence interval. Now, y'all may wonder, right? This file, what file is this? Yeah, y'all ever wonder what is this file? So this file is actually at our course site. The file name is called, can y'all see? Yeah, you can see on the screen, right? So the file name is called EE2006, summary of all things in probability and statistics. And this file is at our course site. All right. So I'm using this file here. So let's start. So we are talking about confidence interval, right? So let's see what it is about. So confidence interval. So of course you see that, well, this make up of two words, right? Got confidence, got interval. Okay. So first of all, it is an interval estimate of a parameter accompanied by a level of confidence. So can you see or not? Yeah, it is an interval estimate. So that's why you got this word interval here. And then the confidence here means that it is accompanied by a level of confidence. Okay, yeah. It is an interval estimate of a parameter. Okay, now this parameter, what is this parameter? Now the parameter here are things like population mean, population variance. So population mean, population variance, they are known as parameter. Okay, yeah. Okay, so well, that's what it is. So it's actually an interval estimate, right? Accompanied by a level of confidence. So for example, you want to say something like this. You want to say that there's a 90% confidence that mu is a population mean, right? So mu lies in the interval 4.5 to 5.5. Okay, so you see, they say something like there's 90% confidence that mu lies in this interval, right? So here, actually, what is the meaning of confidence? Actually, what is the meaning of confidence here? Now, of course, we all know that confidence is an English word, right? But exactly what does it mean here? Okay. So exactly what it means here. So let me ask you a question here. Does it mean that the probability that mu lies in this interval is 0.9? This one, 90% confidence. Does it mean that the probability that mu lies in this interval is 0.9? Class, what do y'all think? Yes, no. So. Yes, no, don't know?
I think so.
Yeah, actually the answer is no. Okay, so the answer is actually a no here. Yeah, in fact, this is a question inside our lecture notes, right? So it doesn't mean this. It doesn't mean that the probability that mu is inside is 0.9. Okay, the answer is no. So if it doesn't mean this, then what does it actually mean? Okay, so what it actually means is not so simple. Okay, it's actually something like that. Now you know, when we calculate this confidence interval, we actually use a sample data to calculate. Okay, we make use of a sample data to calculate. So that means when we get a sample, okay, then it will lead to a confidence interval. Yeah, confidence interval. Yeah, so one sample data will give you one confidence interval. Then of course you know that we can have many samples, right? So then another sample, okay. Then of course that will give you another confidence interval. Okay, yeah. So then you know in our population, we can collect many samples. Yeah, there are many samples that we can take. So meaning what? Meaning that, well, you have so many samples, right? So that means you can also calculate many confidence intervals. Okay, confidence interval is pertaining to that sample data. Okay, yeah. So if you have so many confidence interval, then what is the conclusion? Now the 90% confidence here means that Well, you got so many confidence interval, right? So you expect 90% of them to contain mu. Okay, out of so many confidence intervals, you expect 90% of them to contain mu. That is the meaning. Okay, so in fact, this meaning is recorded in our lecture notes. So what it means is like this. If the sampling process were repeated many times, now sampling process were repeated many times, meaning that you get many samples. Okay, 90% of the intervals obtained would be expected to contain mu. So that is the meaning. All right. So that's why we say something like this. The confidence is 90% that this interval contains mu. All right. So that's the meaning. All right. The meaning is not probability. The meaning is that out of so many confidence intervals, you expect 90% of them to contain mu. All right. As for this particular confidence interval, does it contain mu or not? Actually, you do not know. You just know that 90% of such intervals will contain mu. It's okay? So that's the meaning of confidence. Okay, so that's confidence interval already, right? Then of course, the next thing we come to this page. This one is actually to summarize how to calculate confidence interval. Okay, I think I clicked something here. Yeah. Okay, so now this page here is to tell us how to calculate confidence interval. All right, so it's going to be like a tree diagram. So we have a confidence interval. So we are learning this one, right? Yeah. So we are learning confidence intervals for two parameters. Okay, so confidence interval for mu, population mean, or confidence interval for sigma square, population variance. Okay, so of course below it now we got some details. Now let's look at the confidence interval for sigma square first. So let me show you this. So underneath here, you can see there are 3 points, right? Yep, there are 3 points here. So the first point, this first point here is about what? This one, x is approximately normal. All right, so what it says is x is approximately normal. Now this one is the prerequisite. That means before you go and do this confidence interval for sigma square, you need to have this prerequisite. Well, that's because our theory later on is all based on this. All right, so somehow you must have x is approximately normal. Okay, yeah, so that's the thing. And then the next thing is you need to use a chi-square probability distribution, right? Chi-square. And then the third thing here, well, this one is actually the confidence interval. You're looking at the confidence interval. So you can see that is the lower limit is n-1 s square. S square is the sample variance. And then divide by some chi-square value, right? And here also n-1 s square also divide by some chi-square value. Now these two values, they are chi-square values and they are obtained from the chi-square table. All right, so later on in our problem, we'll actually show how to obtain these two values. Okay, all right, yeah, so that's it. So this is a confidence interval for sigma square. Okay, yeah. Now I want to talk more about this prerequisite here. You see this prerequisite, right? So here you need x to be normal. Now, how to ensure that your x is normal? How to ensure that your x is normal or approximately normally distributed? How do we ensure that? Well, one way is, well, maybe the question tells you, that x is normally distributed. So if they tell you this, then very good. You already got the prerequisite satisfied, right? Then what if the question doesn't tell you this? So another thing is, what if the question doesn't tell you this? Suppose the question doesn't say anything about this. Then how do you make sure that your x is approximately normal? Anyone?
If x is more than 30.
Yeah. A lot of people think that, right? This one, actually, I know that some of you are thinking of what the what central limit theorem is it? Hey, see this file? Can you see this central limit theorem here? Sample size greater or equal to 30 implies what? In class implies what? What is this? X bar is approximately normal. All right, so central limit theorem is on X bar, so it is not on X. Yeah, but a lot of people think that this one is X, right? So I like to point out this one here. Okay. All right, so now you know that one already. So you know that this has nothing to do with central limit theorem, okay? So if the question doesn't tell you this, then very simple. Then you just go and assume that your X is approximately normal. Is it okay? All right, so this one, no theory one. If the question tells you, good. If the question doesn't tell you, then you just go and assume that your X is approximately normal. All right, so I hope you all are clear. Okay, then we go to the next one. So the next one is confidence interval for mu.
Yes, sir.
Yes.
So either way, whether we are told or we are not told, it's gonna be normal for us, right?
You need to have it normal. It is a prerequisite. All right, so if the question tells you, if the question already tells you, then you don't need to assume, right? And they tell you already what? Why do you still want to assume? Then no need to assume. But if the question doesn't tell you, then you go and assume that your X is approximately normal. Make sense?
But how can we assume that? I mean, how can we be sure of that?
You cannot be sure. That's why you assume.
All right.
That's the meaning of assume, right? So that means based on your assumption, then you go and do your calculation. Is it okay?
Yeah, definitely.
Okay, y'all. Okay, now we come to confidence interval for mu. So mu is the population mean, right? Now this one more complicated because there are two cases. All right. So it depends on whether sigma is known or unknown. Of course, sigma is the population standard deviation. All right. So it is known, then one treatment. It is unknown, then another treatment. Okay. So let's look at when sigma is known. Yeah. So here you see, wow, you got 4 points, right? Now the first point, you can see, right? You need X bar to be approximately normal. So this one is the prerequisite. The first point is the prerequisite. So this one prerequisite, okay. And then the second one is tells us what probability distribution to use. They say use Z. What is that? Standard normal. Okay, so when you see Z, then you know that we need to use standard normal here. Okay. Then the third point is actually the confidence interval. So you can see that it's X bar minus E, X bar plus E, right? And then what is this E? This E is called margin of error. Okay, so basically it's X bar plus minus margin of error. And this margin of error is, you see this thing, right? Z something, and then times sigma over square root n. Okay, now this number here, this Z something here, okay, is actually obtained from the standard normal table. Okay, so later on from our problem, you can see that how we obtain this number. Okay, it's obtained from the table. Okay, now, all right, so that's it. So this one is mu, confidence interval for mu, that sigma is known. Okay, now we come to how about when sigma is unknown? And we see that the first point is the prerequisite. You need X bar to be normal. And of course, if you compare here, and actually it's the same. So whether sigma known or sigma unknown, you require X bar to be approximately normal. Okay. And then how about the probability distribution? Now here we use that, right? Here we don't use that. We use T. This one is a T distribution with n-1 degrees of freedom. Okay. And then the confidence interval, well, looks the same, right? It's an X bar plus minus E. But the E is different. Now, if you look at the E, the margin of error here, it is Then you see this one is just now this one is Z, right? Now this one is T, T something. And then times S over square root N. So this T something, this value is obtained from the T table. And of course here you notice that this one is sigma, right? But this one is S. So the S here is actually the sample standard deviation. Okay, now, all right, so it's like this. Okay, now I want to talk more about this prerequisite. They say you need X bar to be normal, right? See, both sides, also you need X bar to be normal. How do you ensure this? How do you ensure X bar is normal? So actually here, let me go to a slide in our lecture notes. All right. Okay. So first of all, we know this, right? X normal implies X bar normal. So this holds for any sample size n. And central limit theorem says what? Here you actually may not have information on X, but what you know is that if you have a big sample size, then implies X bar is normal. All right, so then you realize that, to get X bar normal, actually there are two ways. One way is this, another way is this. All right, so one way is this, another way is this. So let's write this, make us understand better. Okay, so we have this slide here. So this slide is actually a slide in our lecture notes. Well, in fact, you can see the page number. Can you see here, page 276B. All right, so the title is how to ensure that X bar is approximately normal. Okay, so we look at the first point. So it depends on the sample size. So if the sample size is below 30, then what do we do? Well, here, below 30, right? Actually, from the next page, if below 30, can we use central limit theorem? Hey, class, if sample size is below 30, then you know cannot use central limit theorem, right? So that means here we need to use part B. We need to have X normal, then implies X bar normal. Okay, so that is why here we say that if n is below 30, we go and assume that X is normal. Then X bar will also be normal. So this one is, we are actually using part B. All right. Then of course, another case is if your n, the sample size is greater or equal to 30. So in this case, then very easy. You just use central limit theorem and straight away you will get X bar normal. Is it okay? Yeah. So there's a central limit theorem here. All right. So you can see that part B, part C, they are actually used here. This one, n below 30, right? You can use part B. N greater or equal to 30, you can use part C. Is it okay? All right. So now we know how to ensure that X bar is normal already, right? Yeah. Okay. So I think we have enough of summary. Now let's go to our question. Yeah. So this is a question, right? We are actually at tutorial 3, number 2. Yeah, before we go to the question, let me go to our famous slide. This is our famous slide, right? So you will see this slide as long as we do statistics. So this slide tells us how to identify the big X. So what is the big X? So there are two hints. When you talk about mean of something, variance of something, standard deviation of something, your X is that thing. Okay? Or maybe sometimes the question will say something has, well, maybe normal probability distribution. Then your X also probably is that thing. Is okay? So that's how we identify the big X. Yeah. So every time we need to identify the big X. And when you write down the big X, you got to write it in a singular form. Okay, X is singular. Okay, so with this, so we are now ready to do this question. All right, so remember, as we read the question, you try to identify the big X, And also those numbers given in the question, you want to interpret what the number is. Okay, now. Okay, so let's start now. So in the past, it has been found that the standard deviation, you all see this word or not? Standard deviation. Standard deviation of what? Standard deviation of what? Then you can see here, diameter of holes, right? So you begin to wonder lah. Your x is this diameter of holes, right? Maybe, maybe, right? So standard deviation of diameter of holes drilled by a certain machine is 0.04. Okay, so let's stop here for a while. So they tell you that this standard deviation is 0.04, right? 0.04. Now, how to write down standard deviation? How to write down standard deviation? Now, you all know that standard deviation actually got two kinds. One kind is sigma, that's the population standard deviation. Then another kind is S, that's the sample standard deviation. All right, so this number here, this 0.04 here, standard deviation, right? What kind of standard deviation? Sigma or S?
Sigma.
Did I hear someone whisper sigma? Yeah, this one is sigma. All right, this one is a population standard deviation. Is there someone want to ask me why it cannot be sample standard deviation? Why this one cannot be sample standard deviation? Anyone? Why this one cannot be sample?
Why?
Yeah, why? Why this one cannot be S?
They never say anything about sample.
Yeah, correct. Yeah, because you see, from this sentence, the whole sentence until here, there's no mention of sample, right? So no mention of sample meaning that this one is sigma. Is it okay? All right. So let's carry on reading. So the machine has been reset slightly, but there's no reason to believe the standard deviation has changed. So that means your sigma is still this number. Okay, then the next thing is 100 holes drilled by the machine are chosen at random. Okay, and found to have a mean. See mean, no? Mean of what? Mean of x. So what is your x here? Diameter. Can you all see? All right, everyone can see this or not? Mean of what? Diameter. Then just now also diameter, right? So it's quite confirmed that your x is diameter of the hole. Is it okay? All right. And this mean is how much? It's 5.2. Okay, so let's go and interpret the numbers here. Now, first of all, this one, 100 holes drilled by the machine are chosen at random. Wow, when they say something like this, then you know already. Your 100 holes is what? It's a sample. All right, and then your 100 is what? What is your 100? Yeah, class, what is 100?
X bar.
Sample size.
No. They say 100 holes are chosen at random, right? Well, you choose something at random, meaning that you are getting a sample. You're getting a sample. Yeah, so this one is your sample size. So this one is your n. It's okay? So your n is 100. And then in the same sentence, they say that found to have a mean diameter of this. All right, so this diameter is coming from your 100 holes, right? And you see in the whole sentence. So your 5.2, the mean is coming from your sample. So this is your small x bar. It's a particular value, so it's a small x bar. Okay, so this is a small x bar. So next, what do you want? So we want to give an interval estimate for the mean. Okay, interval estimate means confidence interval. Confidence interval for what? For the mean. Confidence interval for mu. It's okay? Confidence interval for mu. And then mean of what? Mean of diameter of all holes with this setting. All right, so you can see mean of what? X. So you can see X is diameter again, right? Just now diameter, then here also diameter, now diameter again. So it's very much confirmed. Yep. And then with a 95% confidence that your estimate includes the true mean. So 95% is the confidence level. All right, everybody okay, y'all? So now let's go and write down all these things. Okay, so this is what we have. So we have sigma, all right? We have n, we have a small x bar, and this 0.95, we call it gamma. That is our confidence level. Everybody okay here? Okay, y'all? Yeah. And what do you want to find? You want to find confidence interval for mu. All right? So let's go back to our this thing here. So confidence interval for mu, confidence interval for mu. Then we know that, okay, yeah, confidence interval for mu. Yeah, so this is where it is. So we got to decide. Yeah, sigma known or not? Hey class, in this question, sigma known or not?
Known.
It's known.
It's known. Yeah, you can see what sigma is 0.04. So that means sigma known, right? So we'll follow this one. Okay, so we are going to have, we need to have x bar approximately normal, right? We are going to use that standard normal, and then your x bar plus minus e, and this is how you calculate your e. Is okay? All right, so let's go and do this. So first of all, we do to make sure that your x bar is normal first. All right, now class, how do you make sure that your x bar is normal?
CLT.
Okay, central limit theorem, that's good. All right, because we all know that our n here is 100, so it's greater than 30 already. So then we just say central limit theorem. So x bar is approximately normal. Yeah, so we've done this one already. And then the next thing is now we need to go and get what now? Go and get this margin of error, right? So actually to get the margin of error is we need to get this z value. You all see, right? We need to get the z value. So let's go and get the z value here. I need to draw a diagram. Where can I draw it? Maybe I draw it at the question there. Okay, so at least here there's a space for me to draw. Okay, now confidence interval, we need to always go and draw diagram. All right. Okay, so let's go and draw diagram. Okay, draw diagram. What to draw? What to draw? So you see here. Oh, they say here use Z, right? Use a standard normal. So that means we'll draw standard normal. Now standard normal is a bell shape. All right. So this one is the bell. Yeah. So this is my bell. So this one is standard normal. So we say that this one is a Z. Okay. So this is N01. All right, now, so not so easy for me to write here. So N01. So this one is our standard normal. All right, so of course 0 will be in the middle. Yeah, so 0 is here. All right. Then the next thing what we do is that we put this confidence level, which is the 95%, right? Confidence level, we'll put it in the middle. Put it in the middle of the diagram. So you see, I go and put here. So the gamma, I put in the middle. All right. So this one is 0.95. All right. So the moment you do this, then straight away, you can tell me these two areas. All right. These two areas straight away, you can tell already. All right. Can you tell me what is the two tail? What is the area of the two tail? Each tail, what is each tail?
Alpha over 2.
No, I want the number. If the middle is 0.95, then each tail is how much?
0.025.
Yes, then you know very well that it's going to be 0.025, right? I wonder Oh, cannot. I cannot type here. So I can only write that. So this is 0.025. All right. This one immediately you will know because the total area is 1. All right. So this side also the same. Also 0.025. Okay, you go and write yourself. Now what we need to know is this number here. You can see this number here. This number that I circle here. This is your number, the so-called Z alpha over 2. Yeah, so this is your Z alpha over 2. Right, so if you use my method, you no need to memorize what is alpha, what is gamma, or that, because everything you see from the diagram. Right, you just need to know that this number is called Z alpha over 2. And you need to find this number from the standard normal table. All right, yep. So let's go to the standard normal table. This side is also 0.025. Write this down. Okay, let's go to the standard normal table. Okay, here is our standard normal table. Everybody can see this, right? Standard normal table. The area shaded is on this side. All right, and this is our Z. Yeah, this is our Z here. So if you compare to what we are having, this is the Z alpha over 2 that you are trying to find, right? So this shaded area here actually is from here until here, right? So it's these two pieces. All right, so what is the total shaded area here? And you can see very well, right? This piece and this piece. So what is the area of the shaded part? Class?
The sum of those two.
0.975.
Yeah, so actually your shaded part here is 0.975. All right, so when you go to your table here, this shaded part is actually 0.975. And you're trying to find this Z alpha over 2 here. Z alpha over 2 is actually a symbol, okay? So you're trying to find this number. So how do you find? Well, the area are tabulated, okay? So you, in your table, you just go and look for 0.975. It's not this page. It will be next page. In fact, can we see 0.975 there? Here. Can everybody see this? There, you see? 0.975. Then straight away you can read off the Z value. What is the Z value? 1.96. Can you all see or not? There, your 0.975 here. So what value gives you 0.975? 1.96. Everybody clear? Yeah, so that's how you get this number. So what is this value? Your Z alpha over 2 here. So it's actually 1.96. Is it okay?
Professor.
Yes.
Can we look at the lower value and then just mirror it?
You mean look at this value? I mean look at here?
Yeah, and then we just mirror it.
Can. This value, if you look for this, it will be minus 1.96. Then you also know this is 1.96.
All right, thank you.
Okay, so anyway, you get this value, the Z alpha over 2 already. Okay, get the Z alpha over 2 already. So in fact, where is it? This file here, right? So once you get your Z alpha over 2, then you go and substitute here, then you multiply sigma over square root n, then you can get your E. And then after that, straight away, you get confidence interval already, x bar plus minus E. All right, so this is how it is done. All right, so you can see that the most important thing is to find the Z alpha over 2. And how I find it, I actually go and draw a diagram to find. All right, did I go and memorize alpha is what? 1 minus gamma, is it? Did I go and memorize that? No, I don't memorize that. All right, so I actually go and find it directly by looking at the diagram. It's okay? All right, so let's see how we do it here. So this is the first step. So we want to get the critical Z value. All right, so this Z alpha over 2 is called critical Z value. So in fact, all these things here, In fact, all these things are actually no need to draw, no need to write. Okay, well, if I do, I won't write all these things, but I will draw this diagram. So this diagram actually is the same as the diagram here, right? Well, not quite the same, about the same. Okay, so I will go and draw this diagram and then go and get the 1.96. All right, so in fact, this diagram is the most important. And then after doing that, then go and find margin of error. So you can see that my Z alpha over 2 is 1.96, right? And then you just put in the numbers. And then after that, your 95% confidence interval for mu is just x bar minus e, x bar plus e. Is it okay? All right, so that's it. So that's this problem. Any problem? Okay.
Okay.
Okay. Yes. So we go to the next question. Yep. So we go to the next question. So next question. Well, once again, we'll try to, as we read the question, we'll try to identify the big X, and also those numbers that are given, we try to interpret them, see what they are. Okay. Yep. Okay. So these are depth perception. Well, that's very important in dental work. And you all know why, right? Because the dentist, you all like dentists or not? Well, I'm always very scared to see dentists. Because dentists will go and drill your tooth, right? And then, of course, because they drill your tooth, then, of course, they must know how deep to drill, right? Because if they drill too deep, then they will drill through you, right or not? So that's why depth perception is very important. So then they have this depth perception aptitude test, right? So they got this test here, and then random sample. This one very clear lah. You see random sample? Now your random sample is what? Oh, there are 14 dentists took the test, and they gave the following errors in their estimation. Okay, and then you've got the 14 numbers here. All right. So let's interpret. Class, you all see this 14 dentists, right? A random sample of 14 dentists, right? What is this 14? What is this number 14?
Sample size.
Yeah, sample size. All right, so this one is actually our n. Okay, that's good. Then another thing I want to ask you is, see here 14 numbers, right? 1.1, 1.5, all that, 14 numbers. What are these numbers? The numbers are what? What are these numbers?
The data.
Yeah, I know data. What kind of data? Is it the height of the dentist? This dentist 1.1 meter tall. Wow, this dentist 1.5 meter tall. Wow, this dentist is very short, only 0.9 meter tall. Is it like this? Is it the height of dentists?
The errors in the estimation.
Yeah, correct. So these data are actually errors in their estimation. All right. Okay. Now this one is your sample data. If your sample data are errors, estimation errors, so meaning that what is your X? What is your X? Your sample data actually comes from your big X, right? So if your sample data are estimation errors, that means your big X is also estimation error. Is it okay? Does that make sense to y'all? Right? Your sample and your big X should be the same thing, right? Okay, so this one actually tells us that your big X is actually estimation error. Okay, right. So let's go and write this down. That's why you see here, X is error of depth perception. Okay, yeah. So let's go and see part A here. Hey, calculate the sample mean and also sample standard deviation. All right, so you're given 14 numbers. You want to find small x bar and also the x square. All right. So this is how you do your small x bar. All right. And this is how you do your sample variance. Yeah, sample variance is like that. And then you go and take square root. That's how you get to your sample standard deviation. So this part, is it okay? Well, actually in your calculator, you have these functions. All right, your calculator, you sure have X bar lah. Okay, as for your this one in your calculator, I think for the S for Casio calculator, they go and write something like this. They go and write something like sigma n minus 1. That's the notation they use. Okay, yeah, so that means this is the S. Is that all right? Yeah. Okay, So now let's go and look at the part B, as to how to input your X. This one you need to go and read your calculator manual. Okay, so now let's go and look at part B. Hey, find a 90% confidence interval. Yeah, so it's a confidence interval for what? For the population mean. Okay, confidence interval for mu. Yeah, confidence interval for mu. And then here they also specify population mean of what? Mean of errors for this depth perception test. All right, so it confirms. Just now we already know that the big X is estimation error, right? Now here it's confirmed. Yeah, the big X is really the error of the depth perception test. All right, yep. So state any assumptions needed. Okay, so we want to find confidence interval for mu. All right, so let's go and see. Go to our just now the tree to see. Okay, so it is still confidence interval for mu, but this time our sigma known or unknown. So just now from our question, we realized that we never write down the sigma, right? Then there's no sigma here. We only got an n. Then later on, we go and get the small x bar, go and get the sample standard deviation, right? But there's no sigma. So that means the sigma is unknown here. Is it okay? Yeah. So this belongs to this case, sigma unknown. Oh. So here we still need this prerequisite. We still want our x bar to be normal. So how to have x bar normal here? How to have x bar normal?
Assumption. Because
Can we use central limit theorem?
Central limit theorem cannot work because sample size is less than 30.
Yeah, here because we know that our n is 14, right? Less than 30. So we cannot use central limit theorem. So that means the only thing is to do what? If n below 30, assume that x is normal, so that x bar is also normal. All right, so that's what we are going to do here. Yep, so let's go and write this. So we say assume x is normally distributed, then x bar is also normal. Is that all right? Okay, so then the next thing, let's go and see what's next. Okay, so this one done already. So we know that we need to use a t distribution. So x bar plus minus e, right? And we need to get the e. And of course, to get the e, the most important thing is go and get the t subscript alpha over 2. All right, and this one is obtained from the t table. Okay, right. So let's go and draw our diagram again. Well, here no place to draw. No place to draw. Well, maybe I draw here. Okay, so let's go and get the T diagram. I want to draw what now? Draw T. All right, how do I know draw T? Because they say here use T distribution. So I'm going to draw T. Now T is also looks like normal. It's also bell-shaped. Then the middle is also 0. Okay, so this is actually T. Right, so maybe I write down here. This one is a T. All right, with n minus 1 degrees of freedom. That means 14 minus 1. So 13 degrees of freedom, right? T with 13 degrees of freedom. And then the next thing what we do is, I'm going to put in the confidence level, which is the 90%. So this time 90%, I'm going to put in the middle, right? So this one is 0.9. And then straight away you can tell already, this part is how much? This part is how much? Yeah, class, someone tell me?
0.05.
Yeah, 0.05. So this one 0.05. The other one also the same. All right, so 0.05. Okay, so now I'm going to write now my T value. All right, now this value here, the so-called T alpha over 2, right? I'm going to write it down. Just remember that it is this value here. This is the value. All right, this is your T alpha over 2. Okay, and this one, the subscript of is actually this area. Okay, the subscript of this T value is actually this area here, which is the 0.05. All right, yeah, the subscript is the area from this point onwards. Okay, so this is your T subscript 0.05. This is our T alpha over 2. Yeah, so now we can go to the T table. So T table, here is our T table. Oh, this is the first time you all see this T table, is it? Okay, now you see here, this is what they call T subscript alpha, right? And you can see very well that this shaded area, the area is alpha. All right, so therefore the subscript of T subscript alpha, the subscript actually means the area from this point onwards. It's okay? Yeah, so it's like that. So here, how to find this value? How to find this T subscript alpha? Everybody can see this alpha is tabulated here, right? You can see what 0.4, 0.3, all that, right? There's a second page. You've got some more alpha there. And then over here, you see this that looks like a V, right? So this one is actually degrees of freedom. This one actually stands for degrees of freedom. All right. So let's go and see. What do we want? Ours is degrees of freedom 13, right? Let me go and put a ruler here. Degrees of freedom 13. All right. Degrees of freedom 13. Everybody can see, right? There, degrees of freedom 13. And my alpha value is the subscript is how much? 0.05. Okay, alpha is your subscript, right? And it is 0.05. Okay, 0.05. So you just bring your finger down until you reach here. All right. So this is the value. Everybody can see or not? So it's a 1.771. Is this clear? Everybody okay? All right. Okay, all. Yep. So we already found the T value. Okay, so we found the T value. Yeah. I want to escape here. Okay, already. Yep. So this is called the critical T value. All right. So actually, all these, if I do I no need to write all this. I just go and draw this diagram, and then straight away get this value as 1.771. Okay. Yeah. So you see, get this value here, and this value is 1.771. You need to draw, a diagram like this, right? So in fact, you need to draw this diagram. So all these actually no need to write. Okay. All right. So you get all this already. You got a T value already. Then after that, calculate the margin of error. Yeah. And see, margin of error is T alpha over 2 S over square root n, right? So your T alpha over 2 is this value. Then your S you calculated already, right? Then just go and put in. Then after that, 90% confidence interval for mu. Well, that's your X bar minus E, X bar plus E. Then you just go and put in. Is it okay? All right, so that's it. So that is a confidence interval for mu. So is it okay? Any questions? All right.
Professor.
So looks like this is also okay.
Professor.
Mhm.
Like, let's say your value is slightly off. Is that all right? Or you might be exactly the same.
What do you mean? Do you mean this 1.771?
No. The final value.
Oh, you mean this one, is it?
Yeah.
About the same. About the same.
Okay, let's say the 1.611 over there. Let's say if I were to be 1.609, is it all right?
Yeah. So I think if we put down 3-4 decimal places will be fine.
All right. Thank you.
Yeah. So okay, y'all. So let's go and do the next question. All right, so here's the next question. So remember, we want to identify the big X, right? So we'll read this together. Hey, so a university admission officer is interested in estimating the variation of GPA. Yeah, everybody see this word variation? Yeah, variation. So what is variation? Variation is what? Now, this variation actually has the meaning of variance. All right, variation has the meaning of variance. So you can treat it like variance of something. So variance of what? GPA. All right, GPA of students. All right, so you got your first hint already. What is your big X? Well, looks like it is a GPA of students. All right, what kind of student? GPA of students in the engineering faculty who has similar results when they applied for admission. All right, so it's a GPA of these kind of students. Right, so that's like our big X. Now we got a random sample of 20 students. Review the following GPAs. All right, okay, what is this 20? Class, what is this 20 here?
N.
What's that?
N.
Yeah.
N.
Yeah, this one is N, sample size N. All right. And then you've got 20 numbers here. So what are these numbers? These numbers are what? What is the meaning? Is it the height of student or weight of student or what?
Is the GPA of a student.
Yeah, and you see here, review the following GPAs. All right, so these numbers are GPA of students. All right, so these are your sample data and your sample data are GPAs. Yeah, so this further confirm that if your sample data is GPA, so that means your big X is also GPA because they must be the same kind of items. Is it okay? All right, so it's kind of confirmed. So the admission officer knows that the distribution of GPAs for such students is normal. I see this word normal, right? I tell you distribution is normally. Then you begin to see, distribution of what? Distribution of X. Yeah, distribution of X. So your X here is what? Can you see? GPA again. So they are telling you that X is normal. And then you want to determine the 95% confidence interval for the population variance. Population variance meaning sigma square. Okay, confidence interval for sigma square. And then they say further, population variance of what? Of GPA of all such students. All right, so it's confirmed many times. Yeah, from here, you already know that X is GPA. And then from your sample data, you also know X is GPA, right? And then you also know your X, the GPA is normal, right? Then another one, your X is GPA. All right, so confirm many times already. So let's go and write it down. So we say X is a GPA of a student in the engineering faculty. All right, and it's given that X is normal, right? So what do you want to find? We want to find confidence interval for sigma square. So let's go and look here. Confidence interval for sigma square. So what is the prerequisite that you need? And you see here, oh, you need x is normal. Is it given? Yeah, it's given. So do we need to assume? Given already. Do we still need to assume? Hey, class, is given to us, right? Do we need to assume further?
No.
Then no need to assume anymore. All right. So we are going to use chi-square table, and this is the confidence interval. So we take a look at the confidence interval. Of course, we'll see the chi-square values, which we'll obtain from the table. But we also see this n-1 s square, right? So we actually need the sample variance. Yeah, we actually need the sample variance, but I don't see it given here, right? They only give us 20 numbers. So that means we must go and calculate. All right. So let's go and calculate the s square. So this is how we get the s square, compute the s square. So we go and get the x bar. And then after that, go and get the s square. Okay. So after we get s square already, then what's the next thing to do? The next thing to do, I think we need to go and find the chi-square values. Yeah, need to find the chi-square values. So let's go and draw a diagram. Hey, let's go and draw a diagram. Okay, let me go and draw here. So what do we need to draw? Draw chi-square. All right. So chi-square is actually like this. It's like a wave. Okay, not? So this is actually a chi-square. Chi-square with n-1 degrees of freedom. Our n is 20, right? Yeah. So this is 19 degrees of freedom. Yeah. So this is a graph. And the next thing is I'm going to put the confidence interval in the middle. Right. What is our confidence interval? 95%. Okay. Yep, 95%. So I'm going to put 95% in the middle. Now this graph is actually slanted, right? So it's like a wave. So what do we mean middle? Actually, middle means the two tails are of the same size. All right, so we'll have a 0.95 here, 95% here. Okay, yep. So then we can tell what are the two tails, right? That's our 0.025. Yeah, 0.025 here. And also need to write 0.025 here. Yeah. Okay. All right. Okay. Now come to these two chi-square values. Well, these two chi-square values are just this point and this point. Yeah, these 2 points here. All right. So I'm going to write them. So I'm going to write them chi-square. And then here also chi-square. It's a small chi-square, not so big. Yeah. So then there's a subscript. As you see here, got some subscript here, right? So once again, there's no need to memorize the subscript. You just see from the diagram. Okay. Now for chi-square, the subscript is actually the area from that point onwards. It's somewhat like T alpha. All right, can you see here? I'm showing you the chi-square table. Can you see this chi-square alpha here? Right, and this area, from this point to the right, is alpha. All right, so alpha is actually the area from that point onwards to the right. Yeah. So now we know the principle already, right? So what is this chi-square? What is this subscript here? Let me see. Oh, here the area here, is 0.025. So that means this area is 0.025. That's the subscript. Can everybody see that? Because this area is 0.025. So therefore the subscript here, same as this area. All right? Then what about this one? What about this point here? Here you also need a subscript, right? But what is the area from this point onwards? Can you all tell? What is the area from this point onwards? What should be this number here?
0.975.
Yeah, it's 0.975 because now this area is a big one. All right, it include this piece. Sorry, I think I clicked wrongly. So it's actually this piece in the middle, plus the small piece here. All right, so you can add 0.95, 0.025. So this is the number 0.975. I hope you can see. So this is 0.975. It's okay. All right. So now you know the subscript already, and you can straight away go and find these two chi-square values from the table. All right. First of all, chi-square with 19 degrees of freedom. Let me go and underline this one. Then you see degrees of freedom 19, right? So that's 19 here. Let me go and put a ruler here. That's my ruler. And then the subscript is what? 0.025 and 0.975. I can see 0.975 here. That's your alpha, right? That's your subscript, right? So another one is 0.025. Yeah, so it's here. Yeah, then you just point your finger down. Okay, so this is the one, chi-square subscript 0.975. All right, and this one, if you point your finger down, then you see this figure, 32.85. That is your chi-square subscript 0.025. Is it okay? All right, everybody clear or not? I certainly hope so. All right, so this is what you have. Okay, so here we want to find critical chi-square values, right? I think on the next page, you see, that's where I draw this diagram. So chi-square 0.025, meaning that this area here is 0.025, right? So the subscript is 0.975, but that's because this area is 0.975. Okay, and all this you can see from the diagram, from the previous diagram. Right? Okay, so now we go and get the values already from the chi-square table. So you see, this is the value, and this one is the value. All right, so it's from here. And then now we are ready to get the confidence interval. So you just see here, right? So this is n-1 s squared over this, n-1 s squared over this, right? So you notice that here, I didn't go and write, don't know which one is which one, right? So how do we know which is which? Well, you get your two chi-square values here, 32.85, 8.9. How do I know which one is which one? How do we know which one is which one?
Whichever one is smaller.
Well, how do I know which one is which one? So first of all, you notice that the numerator, the two numerators are the same, right? Then n-1 s squared, n-1 s squared, same. But because this one is a lower limit, this one is the upper limit, right? So the lower limit, you should divide by a smaller number or bigger number?
A larger number.
Yes, you should divide by a bigger number so that you get a smaller value, okay? Whereas this one is the upper limit, all right? So then you divide by a smaller value so that you get a bigger value. Is it okay? All right, so this is our common sense. Yeah. So you also need not remember which is which, but you just use your common sense. And then maybe you all tell me, hey, what if no common sense? Suppose we have no common sense. Then we put wrongly, then how? You put the 8.9 here, you put the 32.85 here, then how? Well, then never mind. Also never mind. Okay, no common sense, also never mind. Because then your calculator will tell you, oh, this number become bigger. This number becomes smaller. right? The calculator will tell you, right? Then you know already, oh, you put wrongly. And you just go and put it right lah. Okay, now. Yeah, any questions?
Prof, could you show the image just now with the 0.025 and the 0.95? Yeah, this one.
This one?
Thank you. Thanks, Prof.
Okay. Yeah. So, all right, all. So this is how we get the confidence interval. Any questions? Okay, no questions, right? So no questions. We go to some more summary. We go to my summary here. Oh, yeah, at confidence interval, right? Okay, let's see what is the next thing. Okay, so the next thing we are going to talk about is hypothesis testing, right? Hypothesis testing. So we are on to a new topic already, hypothesis testing. So first, let's see what is hypothesis testing. Okay, all right, yeah. So here, hypothesis testing, we are actually testing two opposite statements. Okay, we are testing two opposite statements. Complementary means they are actually opposite. So H0 and H1. So H0, we always call it null hypothesis. And then the H1 there, we call it alternative hypothesis. All right, yeah. So they're actually complementary to each other. However, in the H0, we always go and write equal sign. All right. Well, that means we don't care. We don't really care the meaning. We just always go and write equal sign. Then of course you want to ask me, why you want to be like that? You know, that you don't care the meaning. You just always go and write equal sign. Well, that's because most of the books they do so. So we just follow. Okay, all right, just like that. But for H1, we have three choices. So less than, more than, or not equal. So there are actually three choices. All right. And which one we choose? Well, we need to be very careful, because if we choose the wrong one, then of course our subsequent working, our conclusion, then will also be wrong. All right. So knowing which one to write is very important. So how to know which one to write then? Then we remember our point 2. H1 is the statement that you want to test. Yeah, H1 is the thing that you want to test. All right, now, yeah, so we just remember this. And then later on, when you go to our question, then we will see that how this plays out. All right, H1 is the thing that you want to test. All right, okay, y'all. Okay, then we go to the next thing. Okay, there are 4 steps in hypothesis testing. So it's actually very structured. So these are the 4 steps. So the first step is you go and write down your H0 and your H1. So remember your H0, or you just don't care, you always just go and write equal sign. Your H1, you don't care. You've got to care very much. And you've got to decide whether should you write less than or more than or not equal. Okay, that's the first step. So you got to announce to the world what you are testing. You are testing this H0 and this H1. Announce to the world. And then the second step is that you must calculate something called test statistic. I will talk about this later. And then the third step there is you need to draw rejection region. All right. Now, rejection region means what? Means you reject H0. Okay. So rejection region is if your test statistics falls in the rejection region, then you reject H0. Okay, now, right? This one I also talk about it later on. And then after you do this already, suppose your test statistics falls into your rejection region, then you know you want to reject H0, right? So you conclude. So you want to accept what? You want to reject what? Okay, and then not just that, you don't just say like this. You don't just say, oh, I want to reject H0. Reject H0 means accept H1. Not just like that, not only that, and you want to write in words about H1. And usually our question is like a story problem like that. Okay, so we need to answer to the question. All right. Okay, so this is our conclusion. Okay, now I want to talk about test statistic. And also I want to talk about rejection region. So first of all, let's talk about test statistics and also the assumptions, the prerequisites required for the test. Okay, so I'm going to have our tree here. It's a bit like our confidence interval tree. So we are doing hypothesizing, right? We test two kinds of parameters. So we may test population mean, that's the mu, or we may test population variance, that's the sigma square. All right, so we look at the one for sigma square first. It's simpler. Okay, so you see only 2 points, right? The first point is the prerequisite. That means you need to have this. You see, I need X to be normal. Okay, now if you recall, just now when we are doing confidence interval for sigma square, we also have the same prerequisite. So we require X to be normal. All right. Then the next point is the chi-square. Now this chi-square is what? This is our test statistic. This is our test statistic. So when you're testing sigma square, your test statistic is chi-square. And it is n-1 S square divided by sigma naught square. Okay, and this statistic is a chi-square with n-1 degrees of freedom. All right. Yeah, later on when you go to the problem, you'll see how we calculate this chi-square value. Okay, right. So this is a test statistic. Now let's come to the test for mu. Okay, so here there are 2 cases: sigma known, sigma unknown. Yeah, also something like confidence interval, right? You also have these 2 cases, right? So let's look at the sigma known. So these are the 2 points. So the first point is the prerequisite. So we need X bar to be normal. So you realize that just now the confidence interval one also like this, right? You also need this prerequisite. The second point is the test statistic. So it's the Z. X bar minus mu naught divided by sigma over root n. So this is the Z test statistic. Now, how about for sigma unknown? Hey, then we find the prerequisite is the same. Test statistic is different. This time is the T. X bar minus mu naught divided by S over square root n. Because here sigma unknown, right? So you can't use sigma, so we use the S. So S over square root n. And this is a T with n-1 degrees of freedom. All right. So this slide here actually covers 2 things. The prerequisite and also the test statistic for various tests. Okay, right. So now I will come to the rejection region. Now, rejection region is also known as critical region. All right. So there are actually 3 kinds of rejection region. So we call them upper tail test, lower tail test, two tail test. All right. So let's first look at upper tail test. Now, upper tail test is like this. First of all, why do we call it upper tail? Now, if you look at the rejection region here, you look at the diagram here, the shaded area is the rejection region. Now, this kind of shaded region is called upper tail. So it occurs at the upper tail of the diagram, right? So this kind of rejection region, that's called upper tail test. All right. And when do you get this kind of region? Depends on your H1. Depends on your H1. If your H1 is mu more than a constant, so the key thing here is more than, mu more than a constant, or maybe your H1 is a sigma square, also more than a constant. All right, then you get this kind of rejection region, right? Then the next one is lower tail test. Now, lower tail test is like that. Now, you see the lower tail, right? This is your rejection region. That's why it's called lower tail. And over here, your H1 is mu less than a constant, sigma square less than a constant. then you get this kind of rejection region. All right, so you can see that it all depends on your H1. Then the next one is called two-tail test. I think you can imagine that this one is upper tail, this one lower tail, right? So now two-tail. So meaning that your rejection region is two-tail. Can you see? This one two-tail. All right, and when do y'all get this kind of rejection region? When your H1 is not equal. See, mu not equal to mu naught. Sigma square not equal to sigma naught square. Not equal. Okay, so this covers the rejection region. And not just that. I think you all can see, right? The rejection region, you can see the area. Then here, upper tail test, the area is alpha. Lower tail test, the shaded area is also alpha. When you get the two-tail test, well, because there are two tails, right? So each tail is alpha over 2. And this alpha here got a meaning. Yeah, what is this alpha here? This alpha here is actually called significance level. Right? Usually it's given in the question. The alpha here is called significance level. Okay, what's the meaning of this significance level? Well, this alpha is actually the probability. It's actually the probability that you reject H naught, given that H naught is true. Yeah, probability that you reject H naught, given that H naught is true. So you think about it now. You reject H naught given H naught is true. Is that some kind of mistake? Is this an error or not? Given that H naught is true, but you go and reject H naught. So obviously this one is an error, right? So probability of making this error is alpha, is the significance level. All right, so that's the meaning of alpha. Okay, and because of this, alpha is always what? A big number or a small number? Class, what do you think? Alpha should be a big number or a small number?
Small number.
Yeah, should be a small number because the alpha is the probability of making a mistake. So obviously you don't want alpha to be big, right? So alpha is usually a small number, something like 5% or sometimes even 1%. All right, so alpha is a small number and usually it's given in the question. So it actually controls how big is the rejection region. Okay, yeah. Okay, so I think we have enough. Let's try to do our question. Okay, so now we go and do tutorial 4 lah. Let's go and do the question. Okay, so we'll read the question together. We'll try to identify the big X, and we will also do what? Also go and interpret the numbers given. Okay. Now, a diet program states that the participants are expected to lose over 22 pounds in 5 weeks. Suppose it is known that the standard deviation, I see this word standard deviation, standard deviation of what? X. So is this X or not? Standard deviation of weight loss of participants of this program, right? Standard deviation of weight loss. So standard deviation of weight loss of participants of this program is 10.2 pounds. All right. So standard deviation is 10.2. Hey, I want to write down this standard deviation. Well, standard deviation 10.2. Is this sigma or is this S? Sample standard deviation or population standard deviation?
Population.
Yeah, it's a sigma. This one is a sigma, all right? Because when you read until here, you don't see the word sample, right? So that means this is sigma. Is it okay? Population standard deviation. Sigma is 10.2. Okay, now we come to the next number. Next number is 20 participants. selected at random. Oh, 20 participants are selected at random. So what is this 20 leh?
And sample size.
Sample size.
Yeah. So everyone can see, right? Your sample size is 20. Oh? And in the same sentence, the mean of weight loss is found to be 23.5 pounds. All right, for the same sentence. And participants, 20 participants are selected at random, and the mean of what? Big X, mean of big X. So just now also weight loss, now also weight loss, right? So it's kind of confirmed. So mean of weight loss is found to be 23.5. Why is 23.5? Population mean, sample mean.
Sample mean.
Yep, it's a sample mean. It's a small X bar because it comes from this 20 participants. Is it okay? Yeah, it's one sentence, right? So we must be able to interpret this as a small X bar, 23.5. Oh? Okay, now we come to this sentence here. Wow, this sentence very important. Could this finding substantiate the claim of the diet program? Could this finding substantiate the claim of the diet program? So now they tell you this sample data already, right? Yeah. Could this finding substantiate the claim of the diet program? Oh, can substantiate the claim or not? Test with alpha equal to this, state any assumptions needed. Okay, could this
But
finding
this is H1
substantiate the claim of the diet program? Meaning what? Meaning that you've got to go and test the claim of the diet program.
This is a H1.
Yeah, this is the H1 because you want to test the claim of the diet program, no? Okay, and does this make sense to everybody? You want to test the claim of the diet program, so that will be your H1. Yeah, so that will be your H1. So the claim of the diet program is your H1. Is it okay? All right, all. Okay, so we know H1 is the claim of the diet program.
But they just say directly claim, so it's not equals to, right?
No. We
Because
got to see
they
carefully.
never ask whether it's more than or less.
We just at this moment we know that we need to test H1. We need to test the claim. All right, so our H1 should be the claim. And how do we write down the claim then? Well, we better go and define the X first, because after define the X, we'll get a clearer idea. So we go and define the big X first. So actually we know the big X already, right? Weight loss. Weight loss in 5 weeks of a participant of the diet program. Is okay? All right, so now I'm going to write down the claim. Class, what's the claim of the diet program? You go and read the whole, the whole question. What is the claim of the diet program?
Lose 22 pounds in 5 weeks.
Yes.
Yeah.
Actually the claim is here. The claim is here. Let me highlight for you. Expected to lose over 22 pounds in 5 weeks. And you go to diet program, that means you go in fat, then you come out must be thin one, right? Yeah. How thin there? Oh, must lose over 22 pounds in 5 weeks. Wow, 22 pounds is a very big piece of meat there. You know or not? Can you imagine 22 pounds? Wow, very big piece there. Okay, so you lose so much. So that is the claim. But how do you express your claim? How do you express this claim? Right, I'm going to write H1 there. Right, how am I going to write? And then we go to our summary. Where's our summary? Hey, our summary is here, right? Not here. I want to refer to this. Okay, now you know that we only know how to test 2 items. You are testing population mean, or you are testing population variance. All right, mean of X, variance of X. So in our case, in relating to the claim of the diet program, are we going to test the mean of X or the variance of X?
Mean of X.
What of X? Your X is weight loss, right? Your
Mean.
diet program, it says that lose over 22 pounds in 5 weeks. Expected to lose over 22 pounds in 5 weeks. So to test this claim, are you going to test the mean weight loss, or are you going to test the variance of weight loss? Which one is more reasonable to you?
Mean average.
Yeah. So actually, this one is kind of like intuitive one. So you feel that in order to test this claim, you need to test the mean weight loss. All right, mean weight loss. Well, what does the diet program say there? Mean weight loss is what? How
22
much is the
pounds.
mean weight loss?
22 pounds.
22
than-
pounds. You mean equal 22?
More than 22 pounds.
Yes, more than 22 pounds. So this is the claim of the diet program. Yeah, I hope everyone gets it. So the claim of the diet program is the mean weight loss is more than 22. Lose over 22 pounds. So more than 22. This one, everybody okay or not? I hope okay. Yeah. All right. Okay, so now we come to here. So let's go and write down the diet program. Go and write down the H0 and the H1 first. Okay, so this is my H1. All right, this is my H0. So usually, as you notice in our video, I always write down the H1 first. I write down the H1 first, so I decide that this is a mu more than 22. Then after that, I go and write down my H0, which is mu equal, always put equal. And then the number 22 must be the same, all right? It cannot be 22 here and then here is a different number. No, must be the same number. All right, no? Okay, so this is my H0, this is my H1. So this is actually the first step, all right? And also, actually before the first step, now I know I need to test mu already, right? I need to put down our prerequisite. Okay, test mu. These are the things given, right? Just now we got sigma, we got n, we got x bar, and this is our significance level. We are testing mu under which case there? Sigma known or not? In class, here, I'm testing mu. Is a sigma known?
Yes, known.
Yes.
Yeah, then sigma 10.2, right? So it's under this case, sigma known. Well, whether sigma known or not, I still need x bar to be normal, right? How I make x bar normal? Central limit theorem?
Assume because
Central limit theorem cannot because small sample size. So the only thing here is you need to assume x is normal, so that x bar is also normal. Okay, all right, so that's how we write down. So this is the first step. Put down the H0 and your H1. Your next step is what now? Let me go and see our next step. Next step is what? Calculate test statistic. Okay, and what is our test statistic here? Oh, that's the Z. Okay, so let's go and do the test statistic. Test statistic is like that. Okay, so let me go and put in the values and go and get the value of this. So the value of the test statistic is, I'm going to put in my small x bar. My mu naught here is the 22. Okay, so actually the mu naught refers to this number here, the 22. Okay, the 22 here. Right, so mu naught is 22. My sigma put in, my n also put in. So this is value of the test statistic. So your test statistic here, you put a capital Z, right? Then after you substitute in the values, you put a small z. Okay, yeah, so this is my value. And then now I need to do the critical region, the rejection region. All right, that's the next step. So the next step is to do critical region, not here. Here, the next step is to do rejection region. All right, so I need to draw rejection region. Now, how to draw it? How to draw rejection region? Remember how you draw your rejection region?
Bell-shaped.
See so many kinds of rejection region. So ours is which one? Ours is which one?
Right tail, upper tail.
Upper tail, see more than, right? So upper tail, it's like that. So we see it's like this. Okay, so let's go and draw. Yep, so let me go and draw. So actually the diagram is here. So, but before I show you the diagram, I show you actually how we draw it. So I need to draw what? Oh, test and stick is Z. So that means the rejection region should also be Z. Okay, so this is our Z. Let me type here. So this is our Z and 0, 1. Okay, all right, rejection region. So I already know that upper tail test. So let me go and draw here, upper tail. This one is my upper tail. Okay, upper tail. And the area is alpha. Okay, this area is alpha. I think in this question, the alpha is 0.05, right? Then you just put 0.05 there. Right, so it's like that. And I need to find this critical Z value. Yeah, this is my critical Z value. I think you cannot see here. See? Okay, let me write again. So this is my Z value. All right. How to get this value here? Oh yeah, this one is your 0.05, right? So you can also follow the like your P alpha, Z alpha like that. You can also call this one Z 0.05 because your alpha here is 0.05. It's okay. So this value here, you go and get it from your standard normal table. Okay, let's go to the table. Standard normal. This one, standard normal table. Okay, so now you see here, you see your shaded region is different from this one. So over here, now this one is your 0.05, right? At the moment, this is your 0.05. Yeah, I think I touched the bar there. So this is your 0.05. Okay, so that means your bigger piece here will be how much?
0.95.
Yeah, 0.95. So you go and look for 0.95 in your standard normal. Okay, I think it will be on the next page. 0.95. Where's your 0.95? Here. Can you see? There's a 0.9505. The other one there is 0.9495. And then you ask me which one to take. And then I will tell you, you take either one. Okay, take either one. See which one you like. You want to write 1.64 also can. You want to write 1.65 also can. Of course, you know that our lecture notes we always put 1.65. Yeah, because I like that number better. Okay, but you want to put 1.64. That's also okay. All right, never mind. Yeah. Okay, so we are here. So we got the number already. It's 1.65 or 1.64. So in fact, I write this down. You see, it's my number. I always go and put 1.65, right? I never put 1.64. Right? Okay, so anyway, I put down my number here. So this is my diagram, right? So you can put a 1.65 here. And then our test and stick, this one 0.658, right? Well, obviously, this one 1.65, then 0.658 should be here. So this one is called what? Your test statistics for outside of the rejection region, right? It falls outside, right? So falls outside meaning what? Meaning, can you reject H0?
No.
Yeah, so that means you cannot reject H0. So then you go and write down, oh, you cannot reject H0. So that means you have to accept. So you have to accept H0 and reject the other one. Okay, so this is a conclusion. So you cannot just stop here. Okay, you reject H1. So now I need to go and answer to the question. So this is my H1. That's the claim of the diet program, right? And you are going to reject it. Yeah. So are you going to, could this finding substantiate the claim of the diet program? So you are going to say cannot, right? Because you want to reject H1. So therefore you say we conclude that at 5% level, the claim of the diet program is not substantiated. Okay, so this is your conclusion. Yeah. So you can see that we actually done four steps of the hypothesis testing. So step 1, we announce what is the H0, what is your H1, right? And of course, before that, we must make sure that our prerequisite is satisfied. So step 1, announce the H0 and the H1. Then step 2, we go and do the test statistic. Then step 3, we go and draw the rejection region. And then after that, we see whether the test statistics, whether falls in the rejection region or not, right? So from there, we go and draw the conclusion. Okay, so you can see that it's a very structured one, right? Well, that completes the question already. Any problem?
No.
Okay,
Can we not write like full English? Like we use icon, like all the symbols instead. Like instead of like 5% level, we use at alpha equals to 0.05, or we conclude that alpha equals to 0.05. The claim is blah blah blah.
yeah, sure,
So
you
we
can
just
say
use
that.
the symbol
Yeah,
instead
you
of
can
just
say that. You can say all these things in you using other words. I mean, no need to be say exactly the same words.
okay.
Okay, not okay, y'all. Okay, right. So here we are. So we complete the tutorial already.
Thanks, Prof.
Okay. Yeah, thank you, everybody. So good night.
Thank you, Professor.
Good night.
Okay, good night. Bye-bye.
Good night.